All right, so now we're going to talk about what happens when you vary. It's like the sublevel sets. It's like a critical value. It's like of the problem. Okay, so this is about attaching sort of cells. Okay, so so the point we had sort of talked about earlier is that if you have sublevel sets of some Morse function, and it turns out that the preimage of the interval between those two values, right, doesn't contain a critical point of the function, then the two sublevel sets are diffeomorphic to each other. Okay, so the point is that the situation is different. Right, when we consider regular values. Say a less than b, such that the preimage of the interval from a to b, the closed interval from a to b, is compact as before, but it contains one critical point of f. And the point is that in general, it's like when that happens, then the sort of topological properties, it's like of the sublevel set at A is different from the topological properties of the sublevel set at B. Okay, and in particular, we'll see how you get how you take the sublevel set at A and then sort of glue something to it to more or less give you something with the same homotopy type as the sublevel set of B. Okay, so all right, so let this critical point right be U, and let its index be Q. Okay, so then the claim is that in this case, the homotopy type of the sublevel set associated with B, right, is that of MA, right, which is the earlier sublevel set, with something glued to it with a Q cell attached along its boundary. Okay, so what this means is that if you have BQ, which is a Q-dimensional unit ball, right, with sort of SQ minus 1, the sphere in Q minus 1 dimensions as its boundary, right, what you're going to do basically is that you're going to define a gluing map which identifies this sort of sphere dimension Q minus 1. It's like with the boundary, it's like of MA. Okay, so we define sort of a map G, which is a map from the boundary of this ball, right, to the boundary of this sort of sublevel set. It's like with value A. Okay, and then this has to be continuous. And then, so to sort of attach this ball of dimension Q, right, to MA, right, we identify every point, well, we live at each point X in this boundary of the Q unit ball, okay, with its image, which is just G of X, which is on the boundary of MA. Okay, so the only case which is different is sort of Q equals to 0, and then because SQ minus 1 is empty, so here it's like what you really are doing, and we're attaching now a 0 cell, which is just a point, right? Okay, all right, so anyway. So let me try to illustrate this. It's like with the example we had before, it's like which was the torus, you know, flipped on its side, okay? Right. And then also let me remind you a little bit of, in the two-dimensional case, what the index Q is representing, right? So if you recall the index, right, and then what if you have index 0, right, in 2D, so like I should say in 2D, right, in index 0, you have minima, right, so this, and then index 1 is a saddle, and then index 2 is a maxima. Okay. All right. So you have, again, this kind of sort of donut on its side, right? And then there are a bunch of critical values. So it's like critical points, which I'd called U, V, W, and Z. Okay. And you can easily convince yourself that the index associated with these two values are 1, 1. This is a minima, so it has index 0, and then this has index 2. Okay. All right. So, all right, so as you go from 0, you can go from below, it's like this value, until you hit the critical value, which is f at u. You have index 0, it's like, and we said index 0 means you add a point, right? So as you hit this point, you've introduced a point when you had nothing left. That sort of makes sense. And when you're sort of slightly below, right, you start off with this thing, which is like a bowl, right? And then when you hit this, this has index 1, right? So you're gluing a one-dimensional ball, which is basically just a line, okay? And so what's basically happening is that you're introducing a line which goes this, it sort of pinches it off, right? And then what you end up getting is something, again, which now topologically looks like a cylinder, okay? And then in essence, what happens as you hit W2 is that you again draw a line which connects these two pieces, right? And that has the net effect of giving you something which looks like a hole inside, but still have sort of another hole out here, okay? And then finally, it's like when you hit the Z point, it's index 2. So you glue, it's like a 2 ball, right? And the boundary of the 2 ball is the 1 sphere. So you identify, you know, it's like, so you have something like this, right? And then there's this boundary cap here, which you identified this with this. And then that, of course, just covers that hole up and then gives you the entire torus, okay? So, I mean, intuitively, that, you know, shows you how it's like, knowing something about the index of the critical values or the critical points, right, tells you what you're really adding at every stage between sort of, it's like these critical values. Okay. All right. So let me just stop here for now.